Hello, welcome back to Ask Math Anything. I'm your host, Po-Shen Loh. We're going to talk about some interesting problems today, where interesting means that I don't know what we're going to talk about. If you're new to this channel, I'd like to welcome you. This is a channel where we do a different kind of a math class, where the math class is driven by the interests and the questions of everyone who chooses to show up. Now, I happen to know that most of the people who are showing up and watching this are studying something around algebra or geometry, or maybe they are people who have thought about these things a long time ago. Regardless, what we're going to do is we're going to try to talk about questions where I can give you an answer that's understandable to people who are learning algebra or geometry. If you have been here before, I can tell, because I can see that if you've been here before, I can tell, because I can see that some of you are commenting on the color of my shirt. Yes, I see that we don't have as many people here today, only 95 people so far, but that's also because we have an unusual time. Today we're doing 3 o'clock to 4 o'clock Eastern, and part of the reason is because I'm also working on this Novid app to try to keep everybody safe from COVID-19. Well, let's go ahead and try to get started. What kind of questions do we want to talk about today? Feel free to ask, because as we see things come into the chat, then that makes me think about, that makes me think of something on the spot. I do see that Pietro is asking, will there be an Ask Math Anything with a focus on high school math? Maybe at some point I might do that, but my main interest right now is trying to help bring people into this world of mathematics. In some sense, the people who already are in don't need to be brought in. What do we have here? Okay, let's go ahead and start talking about some of these. There's a question by Raymond Yao asking, can you solve the Millennium problems? Well, there were these 7 problems called the Millennium Prize problems, where you could get $1 million for solving any one of them. The only problem is that they're really hard. I actually myself would not know how to solve them. They are chosen for a reason. They stumped all of humanity. Although some brilliant people are able to solve some of these questions by dedicating a lot of time to do them. So the answer is I myself don't know how to solve any of them. On the other hand, I think that they are great inspirations that help to drive mathematics forward. What else do we have here? Oh, okay. So we have a question here, this is an interesting science question. From Susan Xu. Is it possible to get rid of clovers with math? All right, if I'm going to think about how to use math to get rid of clovers, I think what I would probably need to invent is a lawnmower. I'm just trying to say, what would we do to try to get rid of clovers in general? I suppose that if you figure out a way to make a blade spin around in a circle fast enough, then you'd be able to get rid of clovers. But I'm not really sure I have a better way than that of getting rid of clovers. Their roots grow weirdly, says Susan Xu. Well, in that case, then we have to use a different angle. Maybe we would have to use a biological angle. And at some point, if you're going to do any kind of biological things, say with DNA, that actually also has things to do with math. Because a sequence of these DNA things, A, C, T, and G, that's a sequence. And you can actually think about processing sequences or calculating with sequences, and that becomes math problems. But I myself am not a specialist in getting rid of clovers. What other questions do we have that we can dig in a little bit? What is the question or problem right now, Jason Zhang? We're still trying to figure that out right now because we're waiting for people to ask some good questions that we can bite on and then go dig deeper. Oh, this is neat. FF688 says, could you please help to understand about the values of negative I? Now, negative I is a funny situation. I have a question. Let me see if this works. Yeah, let's try this. And I'll give credit to my colleague Bill Rusha for bringing this up as a question we should talk about. So here, I have a question. Does this work? Let's find out. Square root of minus 1 equals... Can anyone tell me what I should put up here? What should I put up here? Square root of 1 equals something divided by the square root of minus 1 equals something divided by the square root of minus 1. What should I put up there? I should put 1? Are you sure I should put 1? that wouldn't quite make sense, because you see, whatever I put up there, if I just multiply both sides by square root of minus 1, right, then I should get like square root of minus 1 squared, right? So it should be minus 1. So here's a statement that I hope is very clear. There's nobody can argue with this. This is obviously correct, right? Because if I take the square root of minus 1 and multiply both sides by the square root of minus 1, then I get square root of minus 1 squared, which is minus 1 equals this. Okay, so let's simplify this. What's the square root of minus 1? Oh, that's called I. Equals minus 1 divided by I. Okay, is this a problem? Well, actually, maybe this is not a huge problem. Actually, you know what? Maybe I remember this particular one wrong from my friend. From my colleague. So something funny. You were supposed to be able to make something really funny out of this. Is this a problem? I mean, this thing, it's not. It's equal to I. You're saying. So minus 1 over I. Like, what is minus 1 over I? Is that a problem on its own? Actually, no. That seems to be okay. Minus 1 over I seems to be okay. So in that case, this is not a good example. I think that I didn't remember this particular case correctly to give you a good example of how the thing breaks. Is that right? So now you can see I'm thinking. I'm thinking because there's something that we should be able to do that messes this up. Well, okay. I don't actually see anything wrong here right now. This seems to be good. Oh, you're saying multiply top and bottom by it. Let's try that. Okay, let's see if we can do something to make things weird. All right. So I've got the right side, which is minus 1 over I. Let's try the crowd's suggestion. So in that case, that should also be equal to minus 1 over I times I over I. Right? I just multiplied by 1. And if you just multiply by 1, what do you get? You get minus I over minus 1. Actually, that's still consistent. That's not the problem I wanted. So this is equal to I. So far, I haven't actually broken mathematics. So that's not a problem. So there's something that you can do here that would give a problem. So what are we doing? The Pan Am guy, what are we doing? Is we're trying to think about, what might be strange about negative imaginary numbers, like minus I. And honestly, what I'm trying to do right now is I'm trying to think about how I could turn something into, I could turn this into something very, very strange. Interesting. Okay, so I don't have something right now for you, in the sense that I was looking to go and give you something where you suddenly could find that I was equal to minus I. But unfortunately, I don't actually see that off the top of my head. So I'll explain to you why I'm concerned. The reason I'm concerned is because when you write the square root sign, the square root of minus 1 can either be plus I or minus I. It's actually not clear which one of those it is. And when we write the square root sign in general, if I write square root of 16, right? In general, when I write square root of 16, it's well defined. We know that minus 4 and 4 both work. Both would give you an answer. Like minus 4 squared is also 16. Minus 4 times minus 4 is 16. But we say by convention that this is the positive square root. We actually always say that the square root of a number, if we write the radical sign, you write the positive square root. So what I'm trying to break here is that there should be a way to break writing down this notion of square root of minus 1 equals I. And the reason you can break it is because there's no notion of positive or negative with these imaginary numbers. And what you're supposed to do is something like divide by the square root of minus 1. But I don't remember exactly how to fix this. Somebody, Pietro, is suggesting square both sides. If we square both sides, I don't think that's going to be how I can find a contradiction. Right? When I square both sides, I generally will find out like minus 1 equals minus 1. And that won't be as useful. So, yeah, it seems like I can't give you something right now that would break this thing. But multiply by I squared. See, if I do multiply by I squared, I will still get something which looks reasonable. I have to go and dig this a little bit later. I'll give this to you another time. But there's something very fun that you can do with this I, where the minus I suddenly pops up, and you find out that you could just as well have declared that square root of minus 1 was negative I, and then gotten a completely consistent mathematics as well. Okay, but if you're asking about these like positive and negative imaginary numbers, effectively we're just going to say whenever you have the square root of -1, you use I to denote that. And in some sense, you could have a completely equivalent world where you used the other one, like -I instead. Okay, let's see. What else do we have here? Let's move on to another question. I like things asked, what was that ringing in the background? Well, as you know, some parts of America are coming back to work. And so in this particular office, we do have people who are working on other projects. So actually what happened is that a mathematician just came in to work on some aspect of Novid. Actually, a computer scientist. What else can we do here? Oh, okay. Here comes a math problem. Given n married couples, how many ways are there to form pairs consisting of one man and one woman who are not a couple? Okay, I think I understand your question. So you're saying there's n married couples. Let's just draw an example. Suppose there are 3 married couples. And in this particular example, we'll think of the 3 married couples as like there's 3 dots which are marked green and 3 dots which are marked blue. Okay? And they are married in the sense that they're connected to each other like this. All right? So we have these 3 green and 3 blue. Now, the question that's being asked is, how many ways could I pair them up in a different way where every green pairs with a blue, but it's just we've not actually had any of the green-blue original pairs pair together. So the question is, how many ways to pair up so that green goes to blue, so it's always green to blue, and pair up meaning like pair up into 3 pairs. So I have to have each one paired with someone else. All right, so green to blue, and somehow each. So let's just write 3 pairs. 3 pairs. And furthermore, nobody paired to the one that they were paired to before. And nobody paired to same as before. Does the question make sense? So the question is that we have these 3 green dots and 3 blue dots. And at the beginning, each green dot and each blue dot are paired. Okay? And now the question is, how many ways can I mess this all up and then just go and repair them so that every green is paired to a different blue than it originally was? Why would anyone want to do that? Well, I'll tell you a story. So this actually is a very famous problem. This problem is called the derangement problem. So this is called derangements. And it's called derangements because the only kind of person who would do this would be a very deranged person. Not exactly. It's called derangements because you are kind of trying to rearrange in a way that is as not arranged as possible. Wow, Pietro has an answer. Pietro's answer is !n. That might be how you happen to draw. That might happen to be how you decide to write this thing down. But this turns out to have an interesting way of calculating. Now, in this particular example, which I did with 3, I can tell you how to do it in terms of what's called inclusion-exclusion, or it's where you draw a bunch of blobs looking something like a Venn diagram, and you go and try to find out, how many ways have nobody paired to their original partner. Okay? You want me to draw? I'll draw. So the way that we draw is we have to come up with some circles. Okay, I'm just going to draw some circles. The lumps are back. Exactly. We're going to draw some lumps. Okay? So I've got these 3 different pairings. And what I'm going to say is that these 3 green people are called green person 1, green person 2, and green person 3. Okay? Now I'm going to draw a bunch of lumps, since you guys want me to call it that. We've got a bunch of lumps. So I've got one lump here, which is all of the ways where the green person 1 pairs to original partner. Is that okay? So I'll say there's a bunch of these ways. By the way, there's also another lump. There's a lump where these are the ways where green person number 2 pairs to the same original partner. And then we have another lump, which is where person number 3 pairs to the same original one. Does this make sense? So I have these 3 lumps. They're actually called sets, right? And what I'm going to do is I'm making a Venn diagram. Let's start to label this Venn diagram. How many ways are in the very center? So how many ways are there to connect, to pair up greens and blues so that it's in all 3 of these at the same time? Meaning, person number 1 got the original partner, person number 2 got the original partner, and person number 3 got the original partner. How many ways can I do it so that number 1, number 2, and number 3 all got their original partner? What do you think? That one's actually fairly easy. Harry Liu is right. The answer is 1. There's one way. And the reason there's one way is because we're looking at it. That's the only way you can have each one paired to their original partner. Okay. Now, if that's the case, let's try to fill in more of this Venn diagram. The next thing we could try to do is we could try to fill in what happens over here. So inside this almond-shaped piece, this almond-shaped piece is the number of ways that person number 1 paired with their original partner and person number 3 paired with their original partner. I'm going to draw this blue around the almond. How many ways are there in the blue almond? Meaning that 1 got their original partner and 3 got their original partner. What do you think? If I have to make everyone pair with someone, how many ways could I make person 1 pair the original and person 3 pair the original? Also only 1. The reason there's only 1 is because once I told you that 1 was with the original and 3 is with the original, that's it. You know, like there's no choice left for number 2. So in fact, I can fill in over here, this is 0. Are people following me on this? Like, so that's a 1 and that's a 0. In that case, can anyone tell me what goes here? What goes here? How many ways, and here I mean like in that little tiny region there. That's another 0. Harry Liu is right. It's another 0. And it's another 0 because you could imagine another blue almond going around here. And that would be person number 1 and person number 2 getting their original partner. Okay? And then this guy's also 0. Looks kind of like a face. Okay. Next thing. Let's now go and look at the top circle. The whole top circle. How many ways are there for person number 1 to get their original partner? What do you think? Let's give it a color. Green circle. How many ways are there to be anywhere in the green circle? And all that means is person number 1 got their original partner. Well, if you say that, then you say, okay, thanks. Person number 1, you're done. Bye. Person number 1's gone. And then now of these 2, person 2 and 3, they either go across or they swap. So there's 2 ways. So there should be 2 ways in total in the green circle, right? So there's a total of 2 in the green circle. I won't draw that arrow. Instead, what I'll say is if there's supposed to be 2 in the green circle, how many ways are there right there? There's 0 here, there's 1 there, there's 0 here. So how many ways are there over here? I need to add up to 2. So this one becomes 1. And by symmetry, the rest are all like this. So I've now answered the question. So can someone I've now gotten enough information to answer the question. How many ways are there to repair these people so that somehow everyone got a different partner? What would I do for the answer? I filled out this Venn diagram. There are 4 ways. Why? How did you get 4? Did you just add up this 1 plus 1 plus 1 plus 1? So you should just add up the inside? Not quite. It's not the sum of the inside. What we're interested in, repair, you guys are funny. What we're interested in is how many ways can we not have person 1 get their original, not have person 2 get their original, and not have person 3 get their original. This sum of these 4 ones, this 4 here is the number of ways that it's bad, is that somebody got their original partner. So I also need one more thing called the big outside world. The big outside world is like all the different ways of having somehow everyone pick some other partner. Okay? So in that case, how many ways are there? Can someone tell me? How many ways are there? And this big outside region is just called each of the person paired with someone. The universal set in all capitals. Yes, there are 6 ways. So this universal set, oh no, that's my head. I need to get out of the way. Let's draw it over here. This universal set has 6, which is 3 factorial. 3 times 2 times 1. 6 ways to pair at all. Right? So this is just saying I've got 3 people, they're all pairing, there's 6 ways to do this. And if there's 6 ways altogether, and there's 4 over here, the number of ways left outside here is 2. 2 out here. And the 2 is the answer. The reason the 2 is the answer is that's how many ways that the first person didn't get it, the second person didn't get the original, and the third person didn't get the original. So the answer is 2. All right, we did all this work. And so when I have these 3 people, the answer is 2. Now what happens in general? You're saying maybe it's 2 factorial. I'm going to tell you, it turns out the answer is not 2 factorial. The answer is more complicated than this. The answer happens to be, if you do it in general, you can use something called the inclusion-exclusion formula. That's actually a combinatorial formula. It takes a longer class to prove why that's true, so we don't have the time to do that, and we've been spending enough time on this question already. But I'll tell you there's actually another formula you can use. If there are n people, so if there are 3 people, let's do it for 3. If there are 3 people, it turns out that the formula is this. 3 factorial, which is what we just did, but we divide by 0 factorial, minus 3 factorial over 1 factorial, plus 3 factorial over 2 factorial, minus 3 factorial over 3 factorial. Does it work? Let's find out. If I try to simplify this, I get 6 divided by 1 minus 6 divided by 1 plus 6 divided by 2 minus 6 divided by 6. And that's equal to 6 minus 6 plus 3 minus 1, which is 2. Okay, this is a very nifty formula. In fact, if I don't have 3 and if I have more people, you just, you do the same thing. It's like the number of people, factorial, you keep going. It goes minus, plus, minus, plus, minus, plus. And what goes on the bottom is the increasing factorials up until that number. Cool. It is cool. And it's even more cool because of what it gets close to. If I have n people, then it's n factorial. And now I'm going to do this. 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus, and it just goes on for a while. And it's either plus or it's minus. I'll write plus or minus to mean that sometimes it's plus, sometimes it's minus. Strictly speaking, it's negative 1 to the power n, but that's not important, over n factorial. And that's the number of ways. If you're curious how to prove something like this, you use what's called the inclusion-exclusion formula. So it can be done. But this thing over here on the right is very interesting. This thing over here on the right, it tends to get close to a certain number. If you go and take, any old number you like n being 100, and you calculate this, it turns out it looks like e. Pietro says it looks like e. Well, e is bigger than 1, so it can't possibly be e, because the number of ways that I could derange n people has to be smaller than n factorial. It can't be bigger, right? N factorial is the total number of ways to rearrange. That was our 6 before, and our answer has to be less than that. So I can't multiply by e. It turns out that this is sort of like e. It turns out this gets closer and closer to 1 over e. And e is this 2.71828 business. So it turns out that the answer to this question is as n gets bigger and bigger, you get closer and closer to n factorial divided by e. So this is fun. And so your question that you asked turns out to be a very famous one. It's just a question of derangements. All right, so what question should we do next? While we're choosing a question to do next, as you may have noticed, I haven't taken a drink of water yet. And that's because my cup of water is somewhere over there. So let me go and grab that. And I'll be right back, and we'll also do another question in approximately 10 seconds. Wasn't quite 10 seconds because it turns out that my cup had no water in it. My water had no cup in it too. Both are true. All right. What do we have now? What's the next question? Ooh. Mohammed Al-Majid asks, any tips for solving combinatorics questions generally? And what we just saw was a combinatorics question. My general tip is whenever you're counting anything, really write down what you're counting. If you notice, whenever I did these problems, I would always say, here's a lump, and the lump corresponds to all the number of ways to do this. And if you always write down all of what you're actually doing, it makes it a lot easier to count correctly. The biggest issue with combinatorics problems is counting something twice without realizing that you counted it twice, or forgetting to count something. So just be very clear whenever you're writing your scratch work, and it's going to help. Okay. Susan Shree says water to prevent virus. It's true. Supposedly, if you're able to keep your throat moist, it makes it easier to be safe. Actually, we're also trying all kinds of things here, like even keeping the windows open, because supposedly that prevents the virus from just staying inside one place. More questions. Leo Yang has asked, can you recite pi to 500 digits? No, I can't. I don't know enough digits of pi to do that. I never bothered memorizing 500 digits. Ooh, Mr. Eagle Rider. Sir, what is your guidance for students who want to pursue research in maths in the future? Maths. I've also learned maths before. I spent a year studying in England, and over in England they also call it maths. But if you want to pursue research in mathematics in the future, the best thing to do is to not just to do routine problems. It's always to think about why something is true. So you can sort of see, like even the way I'm teaching any of these concepts to you, I don't just tell you here's what we do. It's more of, I wonder if we can think of a way to do this, right? And as long as everything that you're doing, you can think of a reason and a way, then you're basically going through mathematical history. In fact, all of the math that we learn in school is the kind of math that was discovered by people over the years as they thought about the world. And so if you're also thinking about the world, you're basically doing research as of what was cutting edge in the year 1700, which is pretty good. 1700 wasn't that long ago. And then if you just keep doing this, then you end up doing cutting edge research. You end up doing work that was at the cutting edge in the year 1900 or in the year 1950. It's really fun, actually, when you start rediscovering things that were only known to humanity within the last 100 years. Then you could just imagine, wow, if only I could have gone back in time, I would have been a super genius. But that's not really a fair comparison because you have so much more information than they had back then. Back then, by the way, they had no internet. They had no YouTube. They couldn't watch any live streams. But you have a lot of these advantages. So then use them. And then as you go and really deeply think about all the math that you're learning, then it'll be easier for you to make new contributions. Actually, something very exciting. I just saw yesterday that there's this famous problem in combinatorics called Ramsey's theorem, Ramsey numbers. It's like finding, Ramsey numbers are like, it turns out that if you have enough people in a room, then there's always going to be some number of them, maybe like 5 of them, who have all like previously met each other pairwise. Or there's always 5 of them who haven't met each other pairwise. This is a complicated thing. And the question is, how many people in the room do you need to guarantee that for 5? And actually, a guy who was on the International Math Olympiad team, Ashwin Shah, not that many years ago, has just made a major breakthrough on this problem. And this is a famous old problem, and somehow, it takes a relatively new idea to do this. Very interesting. So this is called the bound on diagonal Ramsey numbers. And I saw that there was a recent research paper by Ashwin Shah where he makes a breakthrough on this decades-old problem. And, I believe he's just starting his PhD right now. So it's just showing that how when you take a fresh look at old questions, you might have an insight. Okay. Yes, Ashwin Shah. It's S-A-H, actually, not S-H-A-H. What do we have here? More questions. Solar MC. If I don't like math, should I continue doing it? Why don't you like math? I think that would be what I would ask. You see, if you are learning it in a way that's not as interesting, then indeed you might not like it. But if you look at just about anything in the right way, it ends up being pretty interesting. I mean, I personally didn't always like every subject, but when I finally had the chance to learn it from an interesting person who could explain to me why I should care about it, then suddenly I thought that even this, I found out that even this subject that I thought was boring was really interesting. In some sense, everything that you learn is the product of humans who have gotten really interested in that subject, so interested that they went and did research, that they did historical research or that they did scientific research, and now we have an understanding of that subject. So there was obviously somebody at some point who thought that was interesting. Why? You just have to understand why they find it interesting. And it might not be interesting just to prepare things for exams. That's actually kind of boring. What's the point of the exam? It's to, do an exam and maybe get a score. But the reason why people decided to learn something was to achieve a purpose. And I can tell you, actually right now the reason why I'm so deeply involved in our NOVID ultrasonic distance finding methods is because there's a lot of deep mathematics that's inside there. So right now what I'm finding is that in order for us to actually build something which is effective at stopping the spread of COVID-19, I suddenly need to bring out all kinds of crazy mathematics that I may have thought about at some previous part of my life. And so even though at the beginning you might be like, well, why do I even need to care about sines and cosines? I've been staring at sines and cosines for a few weeks. It's useful. Okay, more questions. Mr. Eagle Rider, I like non-routine maths, but it takes time, and school doesn't allow that. Ah, I see. Well, I think it may be true that you have certain things you're supposed to do in school, and my opinion is that if you're in school, you follow the rules, right? And so you do what the school asks you to do. But your life has more time. You don't only have the time that you're in school. And also your brain, if you decide to make your brain go faster on certain things, then you can get rid of those things faster. So you can actually make sure you have enough time every day to think about some non-routine math. Let me tell you what I did, and what I still do. It's just that all the things that are routine, I will actively attempt to accelerate my pace of doing things, to just get them done, because I don't want to have those things bogging down my time. And then once I've gotten rid of those, then I can go think about something very interesting. This is one reason why whenever anyone tries to write me an email, they seem to find out that I don't reply. That's because I've been intentionally not letting anything else distract me so that I can dedicate enough time to solving the really hard problems. And then when I'm finally done with everything, late at night, I might go and say, okay, let me reply to a few messages. It's just all about trying to allocate your time so that you can get the really important things done. Oh, Mommy and Kids asked, please choose me, but why is math related to coding? The reason is because a computer is really powerful. It can do 1 billion calculations per second. I've been having lots of fun making it do 1 billion calculations of sines and cosines a second over at my computer. But there's only one problem. The computer has no idea what it's supposed to compute. And so you need to be able to tell it instructions. And if you want to achieve things which are more complicated, you need to be able to have more complicated instructions you want to give the computer. If you're curious at all what kind of mathematics is going into the NOVID app, for example, there's a YouTube video on this channel which talks about how a mathematician's insights can help to try to stop the spread of COVID-19. And that will actually reveal some of these ideas that you need to then use a computer to implement. So my answer is, if you're doing coding, you can make coding which is just a web page that shows something pretty. And that's nice. Actually, there's often math in there too. But if you want to go and build an application that's using technology, you often will in fact need to use math to tell the computer what to do so that it can calculate your distances or calculate something else that's useful to you. More questions. Tony Gao asked, C# or CPP? Well, I do a lot of my work in C++, although we then move it into Java and Swift as it starts to run on the mobile apps themselves. Oh, this is really neat. Harry Liu asks, do you think that one day calculus will be taught in elementary school? So it's actually possible. Now the question is, what do you mean by calculus, right? If you mean calculus like the AP calculus exam, which has a lot of problems they're supposed to solve, and all those problems are full of like squiggly things that look like this, if you want to talk about just like how to have everyone do problems like this, to be honest, you could teach someone in elementary school to do this, right? You just tell them, if somebody ever sees something that looks like this, I bet you could go and teach maybe a fourth grader. Any fourth grader can learn that whenever you see this, you take the 2, right? You add 1 to the 2, and you make a fraction out of this. And then you take x and you raise it to there's a 3 and there's a 3, and you write a plus c. I bet you could tell any third grader, fourth grader. Did I say fourth grader or third grader? You can probably tell any second grader. Look, all you have to know is to know how to count, okay? If you know how to count, you can learn that whenever you see this thing, you just write that. But now there's a deep problem. It's like, how do you understand what in the world you just did? Like for a fourth grader or a third grader, you just be like, well, whenever I see a squiggle, an X and a something and a D and an X, you just do this. I mean, I bet that if I drew a bunch of these, you just know what calculus means. If I did this, then what you write is this. I mean, you just give a bunch of examples, right? And then pretty soon you can figure out what the answer is. But okay, that's not actually deep understanding. This is just how you would do an exam. And in fact, when you're actually thinking about the exams, some people don't understand anyway what this is even talking about. They just kind of write this down and they say, yes, that's how you solve the problem. Now, that ends up being a problem if they ever have something like e to the power x. Now, if you want to know, could we have people who are in elementary school understanding the principles of calculus? The answer is yes. In fact, I've had a lot of fun with this. When I'm talking about things like slope, I think that the idea of slope, if you have an elementary school student who's really motivated and wants to learn about the slope of a graph, you can actually go and you can actually explain quite easily why if I took something like this, if I just drew something like this, where I happen to draw all the points like 1, 1, 2, 4, it's like x and x squared. If I draw all of these and I connect them, then, you could actually try to figure out what would the slope be that goes right through this point. And I've always had a lot of fun showing this to people who are just thinking about slope. You can in fact do it without needing any high school calculus. You can just think about the formula for the slope. We actually talk about this in the Daily Challenge course, so I'm not going to go deeper into this. This happens to be one of our lessons. As Jay said, motorcycle went by. Well, I don't think that was a motorcycle. We just happen to live in a college neighborhood. So, not live. This office happens to be in a college neighborhood. And there are a lot of people outside who are college students. For whatever reason, college students seem to like really noisy cars. Maybe it makes it feel like it's going faster. So every so often, if the window is open, you'll hear this really loud car engine from a very happy college student who's like, yeah, I'm going fast and it's going loud. Ah, wait, you live next to what college? Asked Mommy and kids. Well, right now I happen to be in an office which is in the middle of the University of Pittsburgh. Pittsburgh, Pennsylvania is where Carnegie Mellon University is, and that's where I work. But I also have another office which is right in the middle of the University of Pittsburgh, because these two universities are right next to each other. All right, what other math problems can we do here? Oh, neat. FF688. Could you explain the connection between sine in triangles and sine in waves and phenomena like sound? Okay, so I was in fact thinking about this the other day. Sine. What is sine about? So you said sine in triangles, okay? So I'm going to draw for you a circle. Always draw the circle first. Oh, that is a terrible circle. Looks like a lump. All right, here we go. Circle. Maybe a little bit better of a circle. Now, if I draw this circle, I'm going to take the center of the circle. Does that look like the center? A little bit too much to the bottom. Center of the circle. And I'll also draw a triangle. Now, what I've drawn is a very special triangle. Sorry, I've drawn a very special circle. This is a circle where the radius of the circle is 1. Okay, so I've intentionally drawn for you a circle where the radius is 1. Ah, Winter Rain says it's called the unit circle. That's correct. Do you know why it's called the unit circle? It's because this is in the unit about circles. No, it's because the radius is 1 unit. It's a unit. So it's just like, why not? Why would you ever bother drawing a circle whose radius is 32.7? Just draw one with a radius of 1. Okay, so I got this. Now, if I've drawn this right triangle here, it turns out that we have something called a sine. So if I've got an angle here, let's pretend this angle is, what does it look like? I'm going to pretend it's 27 degrees. I don't want to do 30 degrees because I don't want to indicate that this is special. The little circle just means degrees. Okay, so I've got 27 degrees. Now, sine. The sine of 27 degrees is the opposite angle, opposite of the 27, divided by the hypotenuse. That's just what sine is. So in fact, this height here is exactly sine 27 degrees. By the way, that's the entire notion of trigonometry. The entire notion of the sine function is, if I want to know what the sine of 72 degrees is, I draw a right triangle, which has 1 as the hypotenuse, and where the angle coming out of this base is 72 degrees, and the height is the sine of 72 degrees. Okay? So now that's what sine's talking about. Sine is just talking about the right triangle and the height of it if I have a radius of 1. Now, what does that have to do with anything like sound? Well, sound is made by vibrations. Vibrations are when things are going like this, okay? I can tell you a way to make something look like it's going like this. Imagine that you have this beautiful unit circle, and you have a person. And the person is looking that way. That was supposed to look like an eye, but that doesn't look right anyway. So I'm just going to say a person is looking that way. So the person is looking at this circle. Now look at what I could do. If I've got this circle, let's pretend that we are now going to spin something around and around and around this circle. Okay? And what do I mean by spin something around and around and around the circle? Here, we're going to make this ball kind of just keep going around the circle. So it's just going to go around and around and around, right? It's just going to keep going around. Now, if this ball is going around and around the circle, and if the circle is, flat like this, and the person is standing over here, does the person see a circle? Imagine you were just looking at a wheel, like, the wheel is staring right at you. Wheels don't have eyes, but like the wheel is just lined up on you. Would you actually see anything? You would just see like a wheel. You'd see something vertical, right? So if you're just standing here looking, you'd see a wheel which is vertical, looking and it's just like facing you. It looks like a line. Actually, thank you very much, Harry Liu. It would look like a line. From this person's perspective, if they were looking here, all they would see is a straight line. Let's just draw another picture. So what that person would see is, that's the person. From their point of view, there's just this line. And in reality, it's a circle. But from that person's point of view, they just see a line. And what they see on this line is that there is a blob, and the blob is going up the line and then down the line, and then back up the line. Does that make sense? They just see this thing going up and down the line. But now look carefully at what happened with this unit circle. The sine is the height. So actually, here's what's going on. Suppose that this ball is going around this circle at a constant rate, meaning it's just going around and around and around at the same speed at all times. If it's going around and around at the same speed in all times, from the person's point of view, it's doing this. Up, down, up, down. Now, if the person goes and graphs this, if the person goes and graphs the upness or the downness of the ball, it's pretty interesting. Here's a graph. And here is time. And here is the ball. The ball's height or not height. Or height or not height. I mean, it's this, how high up the ball is. It would go up. And then down. And then up, and then down. Oh, and by the way, this in fact happens to be the sine function. Because you see, if I'm going across in time, as I go across this axis in time, my angle is increasing at a constant rate. So basically my angle is going and increasing, and it's changing at a constant rate. So what I'm finding out is what is the height? How does the height depend on the angle? And so, in fact, as the angle is going up, the height is going up and down, and it's exactly the sine, right? So, for example, if I've gone by t degrees, then I should see a height here of just sine of t degrees. And that's, in fact, why what we see here as this wave. This wave is like the thing going up and down and up and down. That happens to just be the height that this particular ball is moving around. So that's actually a very natural connection between vibrations. Sound is also vibrations. This is a sort of an oscillation. It's repeating a pattern. And this thing comes out in a very natural way. You just kind of spin this around and around. And that also happens to turn out the sine function. So that would be one connection between the right triangle, which is what we just drew here, and these waves. And the direct connection is that the sine function is just the height. And so, of course, the height of this wave is going to exactly be the height of this point as it's moving around the circle. So that's one of the connections. Okay, what else do we have here? Haiyan Chang has asked about some more tips on solving geometry problems. I'll give you one big tip. Draw a really good picture. Whenever you want to solve a geometry problem, it really helps to go and draw a picture which is somewhat to scale. Circles are as circular as possible, and then label a bunch of things. Label as many things as you can. You may have noticed that whenever I solve any problem, I like to use a couple of different colors. I like to draw little things saying, okay, that's sine 27. And the more stuff that you label, especially if, as Arav says, make it huge, as you make your whole image huge, you're able to see patterns. You're able to label every little measurement. And after you label so many measurements, you just start calculating all of these different other measurements. So I guess the biggest first hint is draw a picture and then label everything that you can inside the picture. And you might find it. The Pan Am guy also says there's a technique called angle chasing. And that's useful if you're trying to prove theorems about geometry, like for Math Olympiads. And that's sort of the same idea. It's just go and label everything that you can, and at some point you might figure out that you've labeled enough to make a conclusion. More questions. Ooh, Pietro asked, okay, but do waves actually look like the sine function? So it turns out that because of a subject called Fourier analysis, it's actually possible to decompose any sound into these sine function waves. So you can actually always take any sound that you want and then just break it into a superposition or a sum of different waves like this. In fact, that's how a lot of times we will go and try to find out which frequency is most played inside some sound that you're listening to. And if you play the piano, it turns out it's not only one frequency that's going on, it's many different frequencies at the same time. That said, you are right that sometimes there are different kinds of vibrations that are going on. It just turns out that because the sine comes from the unit circle, it's the most convenient to use for this kind of analysis. And indeed, if you go play a flute, the flute wave was not going to be exactly a sine wave. It will be a sum of a bunch of these different waves. Luke Wang, is it possible to make a super fast bicycle using gear ratios? Well, quite probably yes. Like, what would you do? I guess you would try to make sure that you have these gear ratios which are getting more and more intense as you go. So you just keep shifting and shifting and shifting until you can go faster and faster and faster. So in that case, what's the limiting factor, right? If I want to think about what's going to make it hard for you to make a super fast bicycle, do you know what it is? It's actually not. It's not easy just to go and say, add more gear ratio, and I'll just keep shifting and shifting and shifting, and at some point, I'll be able to go like infinitely fast. There are some limits. Does anyone know any limits that might get in the way of you trying to ride a bicycle really, really fast? You know, you can assume that you have these gear ratios, right? You can assume that you can make it so that when you move your leg, then it makes the wheel really go very far. Friction, well, friction, the normal friction is quite controlled because you have wheels. Wheels are doing rolling on the ground. There are ball bearings. Ball bearings are inside like the axle so that there's actually very minimal friction of the wheel. So that's not really the issue. The issue is actually air pressure. There's drag. So this you'll notice if you ever do get on a bicycle which has a really high gear ratio and you try going really fast or go down a hill, what you'll feel is you'll feel this huge wind. You'll feel like you're going through all the wind. In fact, if you pay attention to how those professional bike racers race, has anyone ever noticed that when you have bike racers, does anyone know that when you're racing, you want to basically break the wind for the second person? I'm not sure if you know this, but like somehow they're sometimes like team races or something like this, and then you have all these people on a team, and you basically take turns having somebody in the front of this big chain. What's front for you guys? This is front. In the front of this big chain of bicycles. You're calling it streamlining. No name says it's streamlining. You just go and line up all of these bikers in a row. Somebody's in the front breaking all of the air resistance, and then everyone else is behind it so that they don't have to fight with the air resistance. That first person gets tired, and then they kind of switch back to the other side. Geese do that too. Oh, that's why they're flying in the V, I guess. Wow. Here's a fun thing I don't know the answer to. How did they even know to do this? Like, this is amazing. If somehow instinct and evolution and biology have caused birds to understand that the way to fly more efficiently is to fly in this V shape. I mean, that's just impressive, because how do you even encode that in genetic material? I'm not even sure. Makes me wonder about an experiment of, like, somehow if you just got a bunch of birds and, you know, you just had a bunch of eggs and you just had these eggs hatch on an island far away, would they know that they're supposed to fly in a V? Like, is that like knowledge that is passed on, or is that already built in? And if it's built in, good gracious, how do you build in that kind of knowledge in DNA? That's amazing. Anyway, that's just a secondary thought, right? But so back to your bicycle, you wouldn't be able to go so fast because you would have to suddenly fight this wall of air resistance. And of course, as you go faster and faster, you also break into things like the sound barrier. No one's ever going to be able to break that on a bicycle. But there's something else too. There's something else when you ride a bicycle really fast that makes you really scared. It's that if your road is not smooth, you start to become very susceptible to little bumps. So I know this because I used to bicycle around a lot before this COVID-19 shut everything down. Now I drive. But somehow when I was riding my bike everywhere, if you ride a bike and if the road is a little bit bumpy and you're going really, really fast, every little bump really causes your bike to jump. You know what I mean? Like, if you're just imagining there's some bumps on the road and you're just kind of rolling along really slowly, it's not a big deal. You just kind of go along. But if there's a bunch of bumps in the road, you hit a bump and it goes boom, you know, your bike starts to bounce. And so, in fact, if you have a bicycle, it's very, very dangerous to go super fast because there might be lumps on the road. And if there's one of those, because your bicycle doesn't have like walls like a car and it doesn't have airbags, you could get extremely hurt. Actually, I once bumped into a bump by accident. I got hurt too. I mean, I got thrown off the bike because there was a place I was biking down a hill. I was very excited. I said, I can go really fast down this hill. It's a hill, right? Just go as fast as you can. And then there was an unmarked speed hump. You know, they're usually like painted yellow so you can see them coming. There was one of these humps that was not painted. And so I didn't see it. And I just went down as fast as I could and bam, you know, the bicycle goes flying. That's not good. So now I'm really careful whenever I go down a hill. Unfortunately, I was wearing my helmet. The helmet, by the way, got completely shattered. This is very interesting. This is why I know now you always should wear a helmet. Because if I hadn't been wearing a helmet, something else would have gotten really shattered. And that would have been bad. Okay. More questions. Hi Yan Zhang, you're so funny. Is it possible to make a super slow bicycle with gear ratios? Call me Kevin Lee. Oh, hi, Kevin Lee. Sorry, Kevin Lee, nice question. Can you make a super slow bicycle? Now, you see, the reason why this is not a ridiculous question is because I challenge any one of you to make a bicycle go at 0 miles per hour and stay vertical. I think that's pretty hard. In fact, it's extremely hard to go and make a bicycle that's going to go at 0.0001 miles per hour. Good luck. What will happen to your bicycle? You won't go at 0.001 miles per hour. You'll go at like some number of miles per hour as you tip over. But it's possible with gear ratios. Does anyone know what I'm thinking about? There is a way, if you use gear ratios, and it won't quite be a bicycle anymore. There's something else. Oh, come on. Tricycle is cheating. I don't mean tricycle. I don't mean guide wheels. I mean, there is something else you can do that uses spinning to make it so that you can actually just stay completely vertical. And the answer is to get another wheel. Gyroscope. Yes, Lance is right. I've never tried this at home, so I don't know if this works for sure. Please don't try this at home. This could be very dangerous. But I'm sort of saying, like, I wonder what would happen if you got on a bicycle, okay? So you're sitting on a bicycle, sitting on the seat, but you're not holding the handlebars. Instead, what you're holding is like the axle of another bicycle wheel. And so I'm imagining that I'm basically sitting on my bicycle, not holding the handlebars, holding the axle of a bicycle wheel, and then having that wheel spin really, really, really fast while I hold on to it. I'm not sure my physics is right, but my instinct is that that should help you maintain your balance. My instinct is that if you could actually use your arms to just hold on to that thing, you might be able to maintain your balance. Although now that I'm thinking about it, I need to know more physics, because there's something called precession, in the sense that you would want to start to tip over. But okay, I forgot my physics. I'm not sure if this will cause the axis to try to tilt. But if you could just hold on to it and hold on to it this way, you might actually be able to stay on. Yeah, it's called a flywheel or a reaction wheel. That's what I'm trying to make. However, the reason I said don't try this at home is because I didn't double check my physics. So it could be that this breaks. Although the general principle of gyroscopes and flywheels is that if you could anchor such a thing to the frame of a bicycle and then make it go really, really fast, you would actually be able to maintain your balance. Okay. And by the way, that's the same notion of how the bicycle maintains this balance once you start going. Once you start going, there is that motion. All right, more math questions. What else can we find here? Oh, Picklebot Head has asked, is it possible to multiply pi by a decimal that stops eventually and then get a rational number? So Picklebot Head asks a reasonable question. It's that I've got this number pi. Pi is weird, but is there some other number which like stops eventually, like 172.1314 9, and then you stop there and you get a rational number, which is like 147.216 divided by something small, 214. Well, unfortunately, the answer is no. The reason the answer is no is because if you could do this, the number you've multiplied by here is a rational number too. See? Delete the decimal point and make a bunch of zeros. So if I could do this, then just multiply both sides by this 1 with lots of zeros, goes up there. Divide both sides by this 172 thing, goes down there, and pi has been written as a rational number. So that's why this is not possible. But it's an interesting question. I see that somebody has asked, why did we start early? We started early, unfortunately, because today and today only, we had to adjust the timing of the live stream. I have a phone call coming up that is during our normal live stream time to go and help more people be able to be protected from COVID-19 using our Novid app. So we're basically finishing up the live stream now in 3 minutes. What other questions do we have? Ooh, Harry Liu says, time passes so fast during these live streams. I think it's because you're thinking, right? I mean, presumably it's because you're not just like bored looking out the window, but rather we're really thinking about lots and lots of these different ideas. And honestly, in every single live stream, we just keep touching different ideas all throughout math. Astro Me has asked, how do you compare a ratio? Well, if I'm comparing a ratio, let's start comparing some ratios, okay? What if I give you a ratio like 17 over 21 versus, let's put another number, like 43 divided by 50. Oh, how should I compare these? One way is to take a calculator out and divide both of these and compare them as decimals. But that's usually not great because that when you compare decimals, you might have rounding errors, or it might take a while before you see what's different. Something that's very useful to do if I was looking at this to compare the ratios is I would do the cross multiplication technique. The cross multiplication technique, by the way, is equivalent to saying put them over a common denominator. If you put them over a common denominator, 21 times 50 versus 21 times 50, this one was 43 over 50, so I should times 21. This one was 17 over 21, so I should times 50. All I've done is I've taken each fraction and multiplied by 1. But we call that cross multiplication because I take the 50 times the 17, and I take the 21 times the 43, and I compare them because now they're over a common denominator. And now what would I do? I would go and try to figure out which one of these is bigger. Oh, let's just do it for a fun challenge. How do you multiply by 50? It's like multiplying by 100, but you divide by 2. So let's divide by 2 first. 17 divided by 2 is 8.5, so the top of this is 850. Now this guy over here, 21 times 43, I guess it's mental math time, 20 times 43 is 860. Ah, so this is bigger because 20 times 43 is already 860. 21 times 43 is 43 more. 860 plus 43 is 903, I think. Maybe. Hopefully. So 903. In any case, if I do this, 903 is bigger. So my versus becomes this way. And then this is this way. And this is this way. And I'm done. So I would compare ratios if I wanted to do it without a calculator by just doing this kind of cross multiplication. We basically hit the time, but let me see if I can do one last question and just figure out, figure out what else we can do. Let's do one last question just to close this up. Ooh. Okay. Oh, interesting. Okay, I like this. Yes, we are done. I like to just end with something that we can use to make a few comments. So the last one I'll end with is, this is an interesting one. How would you compare multiple ratios? If you want to compare multiple ratios, in fact, what I would probably do is I would go and calculate decimals, and then it's easier to sort the decimals. If I can't calculate the decimals, here's what I would do. I would take these ratios, and I would start to, like if I had a third one, I would say, I already know that this one is less than that one. Here comes the third one. Let me see where the third one fits in the sequence I have so far. Imagine that you have all of these ratios that you already have ordered, and here's a new one. It's sort of like you're going to the library. And if somebody already sorted the books, and you have a new book, what do? Do you go to the very beginning of the line and you say, does it go here, or here, or here, or here? That's not what you do. There's a smarter algorithm. If there's a whole shelf, and you want to know where this book goes, can someone tell me? Do you go to the beginning and do this, check, 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 check? You shouldn't. What should you do if there's a whole shelf and you have this new number that you want to put in? You should go to the middle of the shelf. Thank you, Grace Yan. And you say, does it go before or after this one? And you say, it goes before. Okay, how about here? Does it go before or after? Oh, it goes after, here. And then eventually you get it. So that is much faster. So that's in fact what I would do. If I had to do this without a calculator and I had a lot of different ratios, I would just start effectively putting them on a bookshelf. And whenever I get a new one, I compare to the middle and I see whether I should go left or right. It's like one of those guess a number games, I have a number between 1 and 100. See if you can guess it. That kind of game. All right. Like binary search. Thank you very much, Fri May. Yes, exactly. Well, in that case, I guess unfortunately we have hit our time for today. If you just showed up because you were hoping that we were going to have a live stream now, I'm sorry, we had to change the schedule for this one day only, and we are in fact finishing right now. On the other hand, we'll be back again tomorrow. If you enjoyed what you saw, we will do more of the same, where what the same means is it will definitely not be the same, because we'll never talk about the same question twice. What will we talk about? There's only one way to find out, and that's to show up and ask math anything. See you tomorrow.